Polymers can be created through a process called condensation polymerization, which involves the chemical joining of monomers with the simultaneous elimination of small molecules, typically water or methanol. This process is different from addition polymerization, where unsaturate monomers such as alkenes link together without the loss of any atoms or molecules. In condensation polymerization, the monomers involved usually have at least two different functional groups that react with one another. For example, a diol, which has two hydroxyl groups, OH, can react with a dicarboxylic acid, which has two carboxyl groups, COOH, to form a polyester, one of the most common types of condensation polymers. The key feature of condensation polymerization is that each time a bond forms between the monomers, a small molecule like water is released. For instance, when a diol and a dicarboxylic acid react to form a polyester, each ester bond that forms between them results in the release of a water molecule. This reaction continues with additional monomers, resulting in a long chain of repeating units and the production of many small molecules as byproducts. A classic example of a condensation polymer is nylon, a polyamide, which is formed by the reaction between a diamine and a dicarboxylic acid. As the diamine and dicarboxylic acid monomers react, they form amide bonds, releasing water molecules with each new linkage. The fundamental difference between addition polymerization and condensation polymerization lies in the nature of the monomers and the process itself. In addition polymerization, monomers with carbon-carbon double bonds, such as alkenes, join together without losing any atoms. This type of polymerization involves only one type of monomer and results in polymers like polyethylene and polypropylene, where the structure is made up solely of carbon and hydrogen atoms, with no small molecule byproducts. In contrast, condensation polymerization typically involves two different types of monomers, each with different reactive functional groups, and always results in the loss of small molecules like water or methanol as byproducts. Condensation polymers, such as polyesters and polyamides, are often more complex and diverse in their properties than addition polymers because the different types of monomers used can introduce a variety of functional groups and structural features. This gives condensation polymers specific characteristics, such as increased strength, flexibility, or resistance to chemicals and heat, which can be tailored for particular applications. For example, polyesters like polyethylene terephthalate, PET, are widely used in fabrics and plastic bottles due to their durability and resistance to stretching, while polyamides like nylon are used in textiles, ropes, and automotive parts for their strength and resilience. Condensation polymerization is a critical process in the production of many synthetic materials that are integral to modern life, from clothing and packaging to engineering plastics and medical devices. The ability to design and create polymers with specific properties through the careful selection of monomers and reaction conditions makes condensation polymerization a powerful tool in materials science and technology.